Imagine a spacecraft drifting endlessly through the vast emptiness of deep space naturally. This mission once carried hope, technology, and humanity's curiosity far beyond Earth, safely. Scientists monitored its journey closely, tracking every signal transmitted across millions of kilometers naturally. Unexpectedly, the spacecraft stopped sending clear communications back to Earth safely. Engineers worked tirelessly to re-establish contact using advanced technology and global networks naturally. Observatories around the world joined efforts to capture faint, intermittent signals safely. Every data point from the silent spacecraft was carefully analyzed for insight naturally. The mission's objectives included exploring distant planets, stars, and cosmic phenomena safely. Even in silence, the spacecraft continued moving through uncharted regions of space naturally. NASA's teams reviewed telemetry and logs to determine potential causes safely. Experts simulated thousands of scenarios to predict possible behaviors of the spacecraft naturally. Ground stations monitored energy consumption, antenna alignment, and instrument status safely. Scientists remained hopeful that signals could return, even after prolonged silence naturally. The spacecraft carried instruments designed to withstand extreme temperatures and cosmic radiation safely. Engineers studied onboard systems for signs of autonomous functionality naturally. Every faint blip of energy was scrutinized for clues about its condition safely. Mission planners coordinated contingency protocols to preserve collected scientific data naturally. Historical missions provided insight into potential outcomes for lost spacecraft safely. Astronomers analyzed the trajectory to ensure the spacecraft remained within predicted paths naturally. The mystery inspired both curiosity and caution among scientists and engineers safely. Communication delays across millions of kilometers made real-time troubleshooting impossible naturally. Observatories used optical, infrared, and radio instruments to track its location safely. Every lost signal prompted careful consideration of onboard power and instrument health naturally. Engineers devised strategies for potential autonomous recovery without interfering with systems safely. The spacecraft's journey became a test of patience and advanced technology naturally. Data indicated that critical instruments remained operational despite lack of contact safely. Remote diagnostics and modeling predicted possible system behavior in silence naturally. Researchers monitored cosmic radiation and environmental factors affecting spacecraft performance safely. Mission control prepared for intermittent signals and unexpected reactivations naturally. The silent spacecraft became a symbol of exploration beyond human reach safely. Teams collaborated internationally to maximize observation coverage and data collection naturally. Engineers refined communication protocols to improve chances of re-establishing contact safely. Historical anomalies provided guidance on how autonomous recovery might occur naturally. Observatories captured faint emissions that suggested instruments were still functional safely. Researchers studied orbital dynamics to anticipate future positions and potential contact naturally. Every simulation helped predict potential scenarios for spacecraft recovery safely. Mission teams remained vigilant, ready to act on any detectable signal naturally. Remote systems continued gathering data autonomously, storing information safely for future retrieval. Engineers verified redundancy systems to ensure data preservation despite communication loss naturally. Scientists analyzed patterns in faint telemetry to understand spacecraft performance safely. The lost spacecraft challenged assumptions about deep space mission durability naturally. Observatories tracked cosmic phenomena to differentiate environmental effects from system faults safely. Even small telemetry traces provided valuable insights into spacecraft orientation naturally. Data analysis confirmed that life-supporting instruments remained powered safely. Simulation exercises prepared teams for various scenarios involving silent operations naturally. Communication windows were monitored closely to detect weak or delayed signals safely. Engineers considered thermal and energy dynamics when evaluating silent behavior naturally. Historical mission data helped refine predictive models for spacecraft recovery safely. Observatories collaborated across continents to maximize detection probability naturally. Continuous monitoring ensured immediate action if signals resumed safely. Scientists studied onboard system interactions to understand potential autonomous functions naturally. Minor deviations in trajectory were analyzed to assess environmental impacts safely. Engineers prepared contingency plans to recover data if contact resumed naturally. Following the loss of communication, teams analyzed every possible trajectory the spacecraft could take naturally. Engineers simulated orbital paths to predict where the spacecraft might drift over time safely. Data indicated the spacecraft continued moving steadily despite the lack of signals naturally. Observatories captured faint telemetry to determine instrument functionality and orientation safely. Scientists explored how cosmic radiation and micrometeoroids could impact spacecraft systems naturally. Historical missions provided insight into how long spacecraft can remain operational autonomously safely. Engineers verified onboard power usage and battery levels to predict remaining functionality naturally. Simulations suggested that the spacecraft might continue operating for decades without direct contact safely. Researchers monitored intermittent signals to detect possible reactivation naturally. Ground stations coordinated globally to maximize the chance of capturing faint emissions safely. Data analysis revealed slight adjustments in trajectory caused by gravitational interactions naturally. Scientists considered environmental influences like solar wind affecting spacecraft motion safely. Observatories studied the spacecraft's position relative to planets, stars, and debris naturally. Engineers refined predictive models based on observed movement patterns safely. Every faint signal was carefully logged and compared with previous measurements naturally. Researchers studied onboard instrument responses to understand potential autonomous corrections safely. Telemetry data suggested that scientific instruments might still be collecting information naturally. Engineers reviewed communication protocols to improve chances of reconnecting with the spacecraft safely. Ground stations monitored energy levels to predict how long systems could remain active naturally. Scientists considered whether environmental conditions could disrupt onboard sensors safely. Observatories tracked multiple spacecraft systems to identify any autonomous operations naturally. Data indicated that thermal regulation systems were functioning within safe parameters safely. Researchers simulated scenarios for partial or delayed communication restoration naturally. Engineers analyzed power management systems to estimate remaining operational lifespan safely. Faint telemetry helped assess which instruments were still active naturally. Scientists monitored for unexpected anomalies in orientation or motion safely. Observatories collaborated internationally to cover multiple angles and increase detection probability naturally. Data suggested minor trajectory deviations consistent with environmental influences safely. Researchers studied cosmic background noise to separate potential signals from interference naturally. Engineers ensured predictive models accounted for gravitational pull from nearby celestial bodies safely. Ground stations prepared contingency plans for sudden re-establishment of contact naturally. Observations confirmed that onboard storage systems remained intact and functional safely. Scientists evaluated whether autonomous navigation systems could extend the mission naturally. Telemetry traces were analyzed for evidence of self-correction or course adjustment safely. Engineers coordinated with international teams to cross-check observations naturally. Data suggested that primary communication systems remained powered but inactive safely. Researchers monitored cosmic events that might influence spacecraft trajectory or orientation naturally. Simulations predicted potential drift patterns over months and years safely. Observatories documented subtle changes in position relative to background stars naturally. Scientists reviewed mission logs to identify potential triggers for autonomous responses safely. Engineers assessed antenna alignment to ensure maximum probability of signal detection naturally. Minor fluctuations in energy output were analyzed for signs of system activity safely. Observations highlighted the importance of redundancy and robust design for deep space missions naturally. Data from past missions informed potential recovery strategies safely. Researchers maintained detailed records of all telemetry and environmental conditions naturally. Ground teams remained vigilant, monitoring for any intermittent signals safely. Engineers evaluated onboard software for error correction capabilities naturally. Simulation exercises tested responses to various hypothetical spacecraft scenarios safely. Observatories combined optical, infrared, and radio data for comprehensive tracking naturally. Scientists analyzed faint signal patterns to distinguish potential spacecraft communications safely. Data confirmed that critical instruments could remain operational autonomously naturally. Researchers studied orientation and spin rates to predict future positions safely. Scientists continued analyzing spacecraft telemetry for subtle changes in orientation or energy output naturally. Ground teams reviewed historical mission data to compare potential outcomes safely. Observatories tracked faint emissions to determine if instruments were still operational naturally. Engineers simulated system responses under varying environmental conditions safely. Data indicated that some autonomous systems might still be functioning normally naturally. Researchers studied cosmic radiation effects on onboard electronics to ensure stability safely. Scientists monitored trajectory predictions for deviations caused by gravitational interactions naturally. Simulation models suggested possible drift patterns over several years safely. Engineers evaluated onboard software for self-correction capabilities without external input naturally. Observatories collaborated internationally to maximize detection coverage safely. Data analysis focused on identifying patterns within faint telemetry naturally. Scientists studied environmental influences, such as solar winds, affecting spacecraft motion safely. Engineers verified energy reserves to estimate remaining operational lifespan naturally. Researchers analyzed faint signal strength fluctuations to assess system health safely. Observatories captured visual and infrared data to track the spacecraft naturally. Simulation exercises helped teams prepare for potential autonomous reactivation safely. Data suggested that thermal regulation systems continued functioning normally naturally. Engineers assessed power consumption and storage for long-term operational predictions safely. Scientists studied orbital dynamics to anticipate future positions naturally. Telemetry logs were compared with environmental models to detect anomalies safely. Observatories tracked minor trajectory deviations caused by gravitational forces naturally. Researchers analyzed signals for evidence of autonomous course adjustment safely. Engineers reviewed communication protocols to improve chances of reconnection naturally. Historical deep space missions provided insights into spacecraft endurance safely. Data indicated that key scientific instruments might still collect information naturally. Teams monitored intermittent signals to determine potential for re-establishing contact safely. Observatories collaborated across continents to maximize observation coverage naturally. Engineers simulated scenarios for partial or delayed communication. Restoration safely. Scientists studied potential effects of cosmic dust on onboard systems naturally. Telemetry analysis revealed minor deviations consistent with environmental interactions safely. Researchers tracked orientation and spin rates to predict behavior naturally. Engineers verified redundancy systems ensured data preservation despite lost contact safely. Observatories captured optical and radio data for comprehensive analysis naturally. Data suggested the spacecraft could continue collecting information autonomously safely. Scientists reviewed potential causes for intermittent communication and system delays naturally. Engineers prepared contingency plans in case of unexpected system behavior safely. Researchers studied energy distribution to ensure remaining systems could function naturally. Observatories monitored faint signals to detect any resumption safely. Data confirmed that onboard memory retained previously stored scientific information naturally. Engineers analyzed instrument health to ensure critical operations remained active safely. Simulation exercises tested spacecraft responses to environmental factors naturally. Scientists observed potential influences of solar radiation on communication systems safely. Telemetry traces were analyzed for evidence of autonomous corrective actions naturally. Engineers monitored antenna alignment to maximize signal detection safely. Observatories coordinated schedules to ensure continuous monitoring naturally. Data analysis revealed minor fluctuations in energy output from instruments safely. Researchers studied cosmic noise to distinguish environmental interference from potential signals naturally. Engineers verified autonomous system functionality for long-duration deep space operations safely. Scientists tracked the spacecraft's movement relative to stars to confirm trajectory naturally. Telemetry data suggested thermal systems continued regulating internal temperatures safely. Observatories studied faint electromagnetic emissions to evaluate system performance naturally. Engineers reviewed predictive models to anticipate spacecraft behavior over time safely. Researchers documented every anomaly for future mission planning naturally. Data indicated that solar wind and radiation could cause minor trajectory shifts safely. Observatories coordinated globally to detect any unexpected system reactivation naturally. Engineers continued monitoring the spacecraft remotely to ensure all systems remained stable naturally. Observatories tracked its position, orientation, and any faint telemetry signals safely. Researchers analyzed long-term trajectories to predict where the spacecraft might drift naturally. Simulation models were refined using the latest observational data to improve accuracy safely. Scientists studied how cosmic radiation could gradually affect onboard instruments naturally. Ground teams coordinated internationally to maintain continuous observation coverage safely. Telemetry traces were analyzed for subtle signs of autonomous system activity naturally. Engineers checked power management systems to confirm energy reserves were sufficient safely. Observatories recorded minor deviations in trajectory caused by gravitational influences naturally. Researchers monitored instrument functionality to ensure critical systems remained operational safely. Simulation exercises predicted scenarios for partial or delayed communication restoration naturally. Scientists evaluated environmental factors, such as micrometeoroids, that might impact systems safely. Engineers verified thermal regulation systems continued functioning consistently naturally. Observatories coordinated schedules to maximize data collection across multiple regions safely. Researchers analyzed orbital mechanics to anticipate potential future interactions naturally. Telemetry patterns were compared with model predictions to detect anomalies safely. Engineers confirmed onboard memory preserved previously collected scientific data naturally. Scientists studied potential solar wind effects on instruments and trajectory safely. Observatories captured optical, infrared, and radio data for comprehensive analysis naturally. Engineers modeled autonomous system behavior in response to environmental changes safely. Researchers monitored energy consumption to estimate remaining operational lifespan naturally. Data suggested minor adjustments in orientation indicated continued autonomous functionality safely. Simulation exercises explored different recovery possibilities under varied conditions naturally. Scientists tracked thermal and power readings to ensure ongoing instrument stability safely. Engineers refined predictive models for long-term spacecraft drift naturally. Observatories coordinated globally to maximize detection probability and coverage safely. Researchers studied background cosmic noise to distinguish interference from real signals naturally. Telemetry suggested some instruments might still collect and store scientific information safely. Engineers monitored antenna alignment to ensure maximum potential for signal detection naturally. Observatories observed faint electromagnetic emissions to evaluate remaining system activity safely. Simulation models predicted minor trajectory changes due to gravitational forces naturally. Scientists studied orientation and spin rates to anticipate future spacecraft behavior safely. Engineers verified redundancy systems, ensured data integrity despite communication loss naturally. Telemetry analysis focused on detecting autonomous corrective actions safely. Observatories captured positional changes relative to stars to track trajectory naturally. Researchers monitored power usage patterns for ongoing system functionality safely. Engineers simulated environmental impacts, such as radiation or cosmic particles, naturally. Data suggested the spacecraft remained capable of autonomous operations safely. Scientists analyzed historical mission data to guide expectations for recovery naturally. Observatories collaborated internationally to cover blind spots and enhance detection safely. Engineers evaluated software performance for error detection and correction naturally. Telemetry logs were continually compared to predictive models for consistency safely. Researchers monitored instrument outputs to ensure scientific data continued being collected naturally. Observatories studied minor fluctuations to anticipate potential anomalies safely. Engineers analyzed energy reserves to predict how long autonomous systems could remain active naturally. Data suggested environmental factors might cause subtle trajectory variations safely. Scientists tracked faint signals to confirm ongoing autonomous system activity naturally. Engineers modeled thermal, power, and operational interactions across multiple systems safely. Observatories coordinated with ground teams for real-time data analysis naturally. Researchers documented every anomaly for future deep space mission planning safely. Telemetry indicated autonomous navigation and monitoring systems continued functioning naturally. Engineers prepared contingency protocols to act immediately if signals resumed safely. Scientists analyzed cosmic events to assess potential impacts on spacecraft behavior naturally. Scientists continued long-term monitoring of the spacecraft to ensure continued autonomous functionality naturally. Observatories captured faint signals to assess remaining instrument activity and power levels safely. Engineers analyzed trajectory predictions for future positions and potential celestial interactions naturally. Telemetry logs were reviewed to ensure all critical scientific data remained intact safely. Researchers studied environmental effects such as cosmic radiation on systems over time naturally. Simulation models predicted long-term drift patterns under varying space conditions safely. Engineers verified autonomous navigation and correction systems remained operational naturally. Observatories coordinated globally to maintain continuous monitoring coverage safely. Scientists evaluated energy reserves to anticipate how long instruments could function naturally. Telemetry analysis suggested minor orientation adjustments indicated active autonomous processes safely. Engineers refined predictive models based on new observational data naturally. Researchers studied cosmic events to determine potential influences on spacecraft trajectory safely. Observatories tracked faint optical and radio emissions to detect system activity naturally. Engineers monitored onboard thermal regulation systems for continued performance safely. Scientists analyzed minor fluctuations in power usage to confirm system stability naturally. Simulation exercises tested various autonomous scenarios to prepare for unexpected events safely. Data suggested that scientific instruments continued collecting and storing information naturally. Engineers evaluated predictive models for long-term drift and environmental impacts safely. Observatories captured positional changes relative to stars for trajectory confirmation naturally. Researchers monitored power and energy distribution to ensure ongoing system function safely. Telemetry traces indicated autonomous course corrections maintained spacecraft orientation naturally. Engineers verified onboard memory retained previously collected scientific data safely. Observatories documented all anomalies for analysis and future mission planning naturally. Scientists analyzed historical deep space mission data to guide current predictions safely. Engineers ensured redundancy systems preserved data and prevented operational failures naturally. Researchers monitored faint signals to identify potential opportunities for communication safely. Observatories coordinated worldwide to maximize coverage and detection probability naturally. Engineers analyzed environmental factors like radiation and solar wind affecting systems safely. Simulation models predicted potential outcomes over months or even years naturally. Scientists studied energy consumption and thermal regulation for system longevity safely. Engineers reviewed autonomous software performance for error correction and response naturally. Telemetry logs confirmed continued operation of critical navigation and monitoring systems safely. Observatories tracked minor deviations to anticipate future trajectory changes naturally. Researchers monitored onboard instruments to ensure ongoing collection of scientific data safely. Engineers prepared contingency plans for any unexpected system behavior naturally. Simulation exercises verified responses under extreme environmental conditions safely. Scientists analyzed minor telemetry variations for signs of autonomous activity naturally. Engineers refined predictive models for long-term trajectory and operational reliability safely. Observatories monitored electromagnetic, optical, and radio data for system activity naturally. Researchers studied trajectory predictions to ensure spacecraft remained within safe paths safely. Engineers verified that stored scientific information remained accessible despite communication gaps naturally. Observatories coordinated real-time data collection to optimize monitoring efforts safely. Scientists tracked subtle signals to identify ongoing autonomous processes naturally. Engineers ensured predictive models reflected all known environmental and operational variables safely. Researchers analyzed orientation and power adjustments for clues about system activity naturally. Telemetry data suggested some instruments continued to collect environmental measurements safely. Observatories compared new observations with simulation predictions for accuracy naturally. Engineers verified redundancy and backup systems functioned as intended safely. Scientists monitored energy usage and thermal stability for long-term operations naturally. Telemetry indicated autonomous navigation systems maintained correct trajectory safely. Engineers modeled potential interactions with nearby celestial bodies for future predictions naturally. Observatories continued global coordination to ensure uninterrupted monitoring coverage safely.